Hey everyone, it's Ms. Cronky here to talk about projectile motion, which is an extension of the parametric equations you covered with Mrs. Homan in our last video. Before I get into the parametric equations for projectile motion, I want to kind of bring back some reminders about some similar problems that we've done in previous courses, Algebra 2, and even in first semester pre-calculus. So we're going to be seeing projectile motion can be modeled by a quadratic, or we've already seen that before in a previous class. So here's two examples that I actually pulled out from the Algebra 2 textbook. In the first example, you've got a jumping mouse, and when you read, you get a model for the jump of the mouse, and then if you pay very careful attention, it says where X is the horizontal distance traveled, and Y is the corresponding height. So there's two things that you know for the mouse. You know it's horizontal and it's a vertical distances. Okay. In the second example that I have on the screen, it's a drum major with a baton tossing it into the air, and it says the height in feet of the baton t seconds after it is thrown. So in this example, you know the vertical distance of the baton and also the time that the baton is at that particular vertical distance, but you don't know its horizontal distance. So in previous problems with projectile motion, we've been looking at it through a single equation, and then we can only really know two things, okay? Down below, I pulled an example from a pre-calculus textbook of parametric equations modeling a projectile motion. And there isn't a story to go along with this one, but notice that you have your X and your Y equation for parametric. So X is going to be like your horizontal distance, Y is going to be your vertical distance. And then both of those are in terms of some t. That's your parameter that you talked about with Mrs. Homan. And that's why on this graph you have those arrows showing the direction or the change in position for your object. And so now we know all three things. We know the horizontal distance, we know the vertical distance, and then we also can find the different times that it's at those particular positions. So that's really key to understanding why we're looking at these two equations instead of just one like we've seen it before. So now we know more information. Here are the two equations that we'll use for projectile motion with parametric equations. So this is for something that we would describe as a projectile, an object that's thrown, kicked, has some kind of push behind it, okay? So that it moves not only vertically, but also horizontally. Notice in these two equations, of course, you have your X and your Y. So the X equation, oops, sorry about that. The X equation is going to be your horizontal distance. So if you're interested in something about how far something goes, you're going to want to know about the X equation. And the Y equation is going to be used for your vertical distance. You might like to think about the Y equation as the height of the object. Okay, so you're going to have an X equals and a Y equal. Both of them are going to be in terms of T, so that's the parameter, and T is going to be time, and the units for time are going to be seconds. Okay, and the reason why I say that it's going to be seconds is because I'm using that -16 in the second equation. Okay. Now there are some other things here in the equations. We've got a V sub 0, we've got a theta, then V sub 0 shows up again, theta again, and then we have an H sub 0. So those things are going to change for different situations or different problems, but they'll stay the same within that particular problem. So let's go ahead and name what all those things are. Let's see, okay, H sub 0, sorry about that. H sub 0 is something that you have seen before in Algebra 2 and also first semester pre-calculus. This we might call your initial height. Another way to think about initial height, because it has that sub-zero, it's your height at time 0, so at the very beginning. If something starts on the ground, the initial height will be 0. If it's being thrown from you, then it's going to be however high it was when it left your hand. Okay. V sub 0 is going to be initial velocity. So when you released the object, at what speed it was initially traveling. And then theta is going to be the angle at which you release the object. And I'm going to say the angle from the horizontal. You might also phrase it, a lot of times you'll see it as the angle of elevation. You might recognize here in this equation, like for x, we have initial velocity times cosine theta. And in the y equation, we have initial velocity times sine theta. Those might sound familiar to you from our chapter 6 unit on vectors. Those are kind of like the horizontal and vertical components. So we're talking about this object being moved to different positions, and there's like two forces working on it, a horizontal and a vertical. Okay. So that might help you think and remember those parts of the equation. Okay, oh, before I leave that, I want to just note that the units on some of these. So initial height would be in feet. Initial velocity should be in feet per second. And then the angle is usually going to be in degrees. Okay, and then if you're talking about horizontal distance or vertical distance, those are going to be answered in feet as well. Okay, let's look at our first example. So in our first example, we're going to do a soccer ball. So you're going to see lots of sports problems today. A soccer ball, sorry, my internet is running a little slow, so takes a while for my screen to catch up. A soccer ball is kicked upward with an initial velocity of 58 feet per second at an angle of elevation of 41 degrees. Consider the position of the ball at any time t if air resistance is negligible. So mathematicians are often going to ignore things like air resistance, wind that might affect the position of the projectile. Okay, so first off, let's write a set of parametric equations to model this. So as I'm reading, I know that I have initial velocity of 58 feet per second, so that's going to be my v sub 0. I know that I have an angle of elevation of 41, so that's going to be my theta equals 41 degrees. And then if you're looking back at those equations that we just wrote down, another thing that you need to know is that h sub 0, the initial height. So you might read through your problem one more time and say, what is the initial height? It doesn't specifically say, so then you're going to have to use some context clues. It's a soccer ball. Where do you normally kick the soccer ball from? A lot of times the ground. So if they didn't say otherwise, I would assume that my h sub 0, my height at time 0 or initial height, is 0 feet. Okay, so now I can write my equations. That's going to be 1 for x and 1 for y. So the x is going to be for horizontal distance and the y is going to be for vertical distance or height. And that's going to look like 58 times the cosine of 41 and then t. And I like to just protect that with a set of parentheses because that's really just like a number. If you type it into your calculator, you get some decimal. So some number times t. And then for y, it's going to be negative 16t squared. And then we're going to use that vertical component of velocity. So that's going to be 58 sine 41. And again, I like to protect that with a set of parentheses. Okay, not totally necessary, but know that that's a number. And then plus the initial height. You could write plus 0 here, but I'm not going to write that because we don't really need it. It says draw a model of the situation. You can use your graphing calculator. So I think in Mrs. Homan's video, she might have showed you how to do it in the graphing calculator. I'm actually not going to do it in the graphing calculator because it's going to take up some time. And more importantly, that you can like imagine the picture here is the thing that you want to be careful of. So I'm going to draw myself a little picture. Here's my soccer player. There's the ground, here's my soccer ball, and we're gonna kick the ball. The ball is gonna go up, and then the ball is gonna come down. Okay, so that would be a very similar image that you would see in the graphing calculator. It's going to be an upside down parabola. Okay. On the graphing calculator, of course, you would have an X and a Y axis. So if I draw those in right here, the X and the Y axis are going to be, I'll use right here. So we're starting right there, so that where the ball is, that's our origin. Okay, so there's our X and our Y axis. Now, what I want you to think about is, like, when you look at this picture, if you were to see this in the graphing calculator, or you were thinking about you're at a soccer game and you see the kick happen, what's something that you would wonder about that soccer ball and the kick? You might have these questions. How high does the soccer ball go? How far does the soccer ball go? How long is the soccer ball in the air? Right? Those are all really great questions. So I'm going to start with that first one, which is how high, okay, does the ball go? Another way to phrase that is, what is the max height? Okay, so hopefully in your picture, you can see where that happens. Okay, that's up at the top. That we know is our vertex. Okay. And I wanted to do this one to kind of remind you of a special tool that you had back in Algebra 2. In Algebra 2, if you wanted to find the vertex of a parabola in what we called standard form, ax squared plus bx plus c, then to find the vertex, to get the x coordinate, you would do the opposite of b over 2a. Oh, sorry, you can't see that. Okay, the opposite of b over 2a, and then whatever you got for that x, you would plug it in. So I'm going to say f of opposite of b over 2a, like function notation. Okay, but the most important part about that is this opposite of b over 2a. So that's going to get you the horizontal x, okay, for when you reach your max height. So you know, if we're thinking about max height, or how high does the ball go, that has something to do with our y equation. So I'm going to be working with the y equation on this one. Y equals negative 16t squared plus 58 sine 41t. And this could be, we can think about it like our ax squared plus bx plus c over here. Okay, a is negative 16. B is that 58 sine 41. And then C must be 0. Of course, that was our initial height. So we want to find the max height. We first have to find when the ball reaches its max height. So we're going to say T equals the opposite of B, so negative 58 sine 41. And then we're going to divide it by 2a, which would be 2 times negative 16. Now, if you're going to type that into your calculator, a couple of things. Make sure you're in degree mode. And then if you're going to type it all into your calculator at one time, make sure you do 2 times negative 16 in a set of parentheses. Otherwise, you can, an easy way to avoid that is to divide by negative 32. Okay, so I'm going to type that into my calculator over here. Divide by negative 32. I get something like 1.189. See if you can get that, 1.189 seconds. So that's telling me at the vertex, t is 1.189 seconds. How will I get the actual max height? I'm using that y equation. I'm going to plug that t in. Okay, so I know when it reaches its max height. Now I want to know what its max height is. So I'm going to do negative 16 times 1.189. And oh, on your calculators, if you don't want to type in 1.189, remember you can do the answer button. So negative 16 times the answer, that's second negative, plus 58 sine 41, and then times your answer again. Okay. You do want to be careful here on this sign 41. I know the calculator will bring up a set of open parentheses, so make sure that you close it. If you did a set of parentheses around the 58, then you'll have a double close right there. Okay, so it all depends on how you type it in. If you're going to use 1.189 instead of the answer key, your answer may be slightly different, but it should be pretty close. I'm going to use my answer function as I type this in. And I find out that my max height, my Y value, is 22.62 feet. So the 1.189 is when it reaches its max height. The 22.62 feet is its actual max height. Going back to our picture. Okay. Another question that you might have wondered about this is like how far does the ball go? Okay, so you might be wondering, you know, like how far down the field did they kick the ball? Okay, so this would be like an X that you're trying to find. So you would use the X equation. Now, you're kind of interested in this point over here, really, because that's when the ball hits the ground. And we don't really know what X is. We don't know how far it is. We don't really know when, right now, it hits the ground. But we do know something at that blue point. We'd like to know its time. But right now, what we really know is its Y value. If you're there on the x-axis, then your Y value is 0. So even though we're interested in how far the ball is going, so we're interested in the X, we're actually going to start with the Y equation and then solve for time when the ball is on the ground and then plug that in to find our X. So some of these you might have to think about, like, how can I get the part that I want? So we're going to actually use the Y equation, okay, to say how far the ball goes. At some point, we know we want to use the X equation. X equals 58 cosine 41 times T. But first, we need to know what that T is. We don't know. We're going to set Y equal to 0. And we're going to solve for T right here. Okay, in the Y equation. Now this one's really nice because my initial height was 0. So I have two terms that are being added over here, and I can just factor out a T. So 0 equals T times negative 16T plus 58 sine 41. And then if I factored, make sure one side is equal to 0 first. If I factor, to solve by factoring, I just set my factors equal to 0. So I get T equals 0, negative 16T plus 58 sine 41 equals 0. So then I would subtract the 58 sine 41 from both sides and divide by the negative 16. So that's going to give me, let's see, 2.378 seconds. Okay, so that's when the ball hits the ground, but remember, we're trying to find when the ball hits the ground, we want to know how far it actually went. Okay, so in this, we're going to take this time and we're going to plug it into the X equation. Okay, so to answer the question how far the ball goes, we're going to say X equals 58 cosine 41. Sorry about that. And then times 2.378. And I'm going to use my answer key again on this one. So if you're using 2.378, we're going to have slightly different answers. Okay, I get 104.1 feet. Okay, so that's how far the ball goes. Okay. I know how long it's in the air. That's this piece right here, 2.378 seconds. Like I said, we did the max height and the time of the max height. Some people might recognize that there is some kind of symmetry on this one. So if it reached its max height at 1.189 seconds, then we could just double it, and that would be the time that it hit the ground, and then we could plug that in. That only works if your initial height is 0. So just be really careful with that. I'm going to do one more example where the initial height isn't 0. So we're going to have to use a different method to solve. Okay, so let's look at that last example. Okay. Okay, so in this example, we've got a shot put released from a height of 6 feet at an angle of 43 degrees from the horizontal with initial velocity of 40 feet per second. So we want to write the parametric equations. And remember, you'll always have an x equals and a y equals. X for the horizontal distance, y for the vertical height. So x equals the initial velocity, which is 40 feet per second, times the cosine of 43 degrees. And then that's just a number times t. Okay, oops, looks like you can't see what I'm writing. So let me stop and reshare my screen. Okay, there it is. And then for the y equation, that's going to be negative 16 t squared plus 40 times the sine of 43. Remember, this is vertical height, so I want that vertical component, t, and then plus the initial height, which on this particular problem, we have an initial height of 6 feet. So we're going to have a plus 6. Okay, so if you're thinking about an image here, we've got a shot put, going to release it, and then it's going to land on the ground. Okay, something like this. And if you're thinking about the x and the y axis, we have our x-axis, we have our y-axis, and the big difference with this problem that you'll want to watch out for is where that starting point is, so that initial height. At time 0, okay, or 0 distance from the shot putter, we have an initial height of 6, so that's when t equals 0. And the one thing that you would have to be careful of is you can't use any of the shortcuts where maybe you would just like double the distance to the time to the max height and say like that's how long it was in the air, because there's a little portion to the left of the shot putter that makes this not symmetrical through the vertex. So to be careful with that. So I want you to think about, if you were watching shot put, what is the most important part of shot put? That should be how far the shot put goes. Okay, so that's the big point, how far the shot put goes. So I'm going to ask the question, how far does the shot put go? Okay, so what is the distance of their throw? And so again, we did a problem like that before where we asked how far something went. That's horizontal distance. We're interested in this 40 times cosine 43 t. But in order to be able to answer that question of how far it goes, we have to know what t is, and we don't know t. Okay, we're interested in this horizontal distance right here in blue. This is the x we want to find. We'd like to know what time it is when the shot put is there at its furthest distance. Well, that's when y is equal to 0. So we're going to do that whole piece where we actually go through the y equation first, setting y equal to 0. 0 equals negative 16 t squared plus 40 sine 43 times t plus 6. And then we're going to solve that. And the big difference here too is we can't just factor out a t like we did in the last example, because we have A is equal to -16. We have B equals 40 sine 43. And we have C equals 6. This last term doesn't have a T in it, so we will have to use the quadratic formula. So you remember the quadratic formula, x equals -b plus or minus the square root of b squared minus 4ac all over 2a. For those of you who don't know me, I am a little bit tone deaf, but I feel like I do pretty good with the quadratic formula. Okay, so we're going to be plugging into that quadratic formula with these values for A, B, and C. And notice like B is not really a nice number, 40 times sine 43. I don't want to turn it into a decimal because it's probably a long decimal. I don't want to round it in the middle of the quadratic formula. So I'm going to actually pull up my graphing calculator and share that screen now so that I can show you or remind you how to store a number that you can use, and we'll do the quadratic formula together. So we're trying to solve for when the shot put is on the ground, when its height is 0. Okay, so make sure because you're doing the sine of the 43 degrees that you're in degree mode, and it doesn't really matter if you're in function or parametric right now. So I'm going to go ahead and get to my math screen. Okay, I'm going to take that B value, which is 40 sine 43. I'm going to type that in, and I'm going to go ahead and evaluate that. So it really is 27.27, lots of stuff. But what I'm going to do is down by the 1, there's a button on the left that says STO with an arrow. That's for store. So I'm going to click it, and then you can tell it any alpha letter you want to store it as. Since this is my quadratic formula and this is going to be my B value of the quadratic formula, I'm going to do alpha, and then I'm going to choose B, which is the apps button. So it's saying take this answer, 27.27 stuff, and store it under B. And then I hit enter and it's stored. So now when I want to do the quadratic formula, every time I want to use that 40 sine 43, I can just call up B and it'll put that number there for me. So it's going to be the opposite of B. So I'm going to use the negative. Make sure you're using the negative by the decimal, not the subtraction by the 6. Negative B plus or minus. Now you can do a little bit of think ahead right here. You're going to be dividing by 2a, where a is -16. So you're going to be dividing by -32. You need your numerator to be a negative number so that you get a positive answer that makes sense for time. So I'm going to choose negative B minus the square root in hopes that I'll get a negative answer here. And then it should be B squared, so alpha B, and square it, minus 4 times -16, times our C value, which I think is 6. And I didn't protect this with parentheses, where if I wanted to do the whole quadratic formula, because I have that minus in the numerator, I would need a set of parentheses. I'm just going to go ahead and hit enter. Look and see that my value is negative, so I'm going to divide by 2a. If you're going to divide by 2 times a as 2 times 16, make sure, notice I opened a set of parentheses to protect it. You can avoid that whole issue if you divide by -32. So -60.868 divided by -32 gives us 1.902. So this is the time when the shot put hits the ground. If I go back up to that negative B plus or minus, and let's say I choose the plus, so I'm just going to go over and rewrite and change this to a plus. Notice that 6.3 is positive. When I divide it by the -32, I would get a negative time, which doesn't make sense. That's the part where it would be on the ground, like on the other side of the shot putter. So we want the positive one, the 1.902. So let's remember that and carry that over. 1.902. from our calculators. So we know that t equals 1.902 seconds. Okay, and that's when the ball, so if we come back up here to our picture, that's when the ball is at a height of 0. Okay, the other one, the -1, is on the left of the y-axis, so it doesn't make sense. And we want to know, remember, how far the ball went, so we're going to plug that value back into the x equation. Okay, so I have my x equation right there. X equals 40 times cosine 43 times 1.902. I'm going to do the rounded version because that's on my calculator on my computer, and I don't have that on my calculator over here. So I'm going to type in 40 cosine 43. Make sure you close that parenthesis, times 1.902. And it looks like the shot put goes 55.64 feet. Okay, so that's how far the shot put went, which is a pretty good throw, as I understand it. Correct me if I'm wrong. Okay, so the point being there, sometimes you might have to use this quadratic formula. A lot of times with this quadratic formula, you're going to get a not so nice b value. So using that store function in a calculator is really nice. And then you might need to take that time and plug it back in so that you can find your horizontal distance. All right, good luck on your homework. Stop into office hours or email us if you have any questions. We're happy to help. And have a great day.